The third meta-heuristic that I want to get you familiar with is the genetic algorithm. It uses the analogy of Darwin's theory of evolution with the survival of the fittest and natural selection. So now we are looking at populations of solutions rather than just dealing with one trial solution at a time that we have done for the taboo search or also for the simulated annealing approach. You remember that we said with respect to our Kevin on his island that he is searching alone on his island. But if we would consider populations of solutions and search, then we would faster get to the highest hill on the island. So if we drop Kevin here or there, and if we then drop other members of the population in other spots of the solution space, then our genetic algorithm can convert faster to find very good solutions for our problem at hand. So the thing is now we want to generate populations that we will then improve to, or the populations are our trial solutions. We now consider more of them, and we want to improve then our solutions so far. Now there is another method that is drawn from genetics, which is mutations. At a certain step of our population, we want to enrich the gene pool once again, so we allow mutations to occur. That means that parents can inherit, or children can inherit also features from the parents that have not been there yet or have not been inherited so far. Let's see how we can implement this in our example. We once again look at the traveling salesman that we have done throughout the lecture, and now we want to consider how a genetic algorithm would work with that. So here is the general rules that how a genetic algorithm works. So we are working with populations or parents to find now new trial solutions. The parent selection is according to the fittest members of those, or the features of the fittest parents. And parents are then paired randomly together to generate children that inherit features of the parents. At a certain stage, some time in the process, we will allow mutations to happen. So there are features that get to the children that have not been yet there in the parents. So in order to get on with the algorithm, we have to define or answer once again some questions that are stated here. So which population size should be used? How should the parents be selected? How should the children features then be derived from their parents? And how should mutations be injected as well? And when would we stop the algorithm of working, so that we take the solution that has been found then as best? So for our example on the TSP, we define the population size to be 10 parents. And this number of combination with the cities that we have at hand, we have 7 cities, is a really our example is quite small for such a huge population size of parents. Then we have the rule of parent selection. We take 5 of the fittest members of these trial solutions. We select 4 of them randomly then to become parents. And the 5 least members of this population are then, from those we select 2 of them randomly to become a parent. And then we pair up 6 pairs or couples of parents to get children then. The passage of feature inheritance or gene inheritance from parents to children needs to be defined then highly according, or very specifically according to the problem at hand in general. We will see how this is done for our example. And we consider a mutation rate to be 0.1 probability of mutations of inherited features into the opposite feature. And the stopping rule is after 5 consecutive iterations without any improvement. So in the Excel table now, I show you how to generate the first 2 parents for the inheritance process. Not 10 of them, because it's quite extensive. I will show you how this is done by our OR tutorial from our textbook. But consider this. We have the initial trial solution given here. That is also the one we were working with continuously, where we have a total distance of 69. Now we consider for the inheritance, or for generating the first parents, we consider our hometown where we start. And from this hometown now we can select the following 3 cities to be inherited by or to be formed by the parents. So for instance, we can go from city 1 to 2, 3 and 7. Then we would select, and this is how we build up the sequence, from the various cities we have more options to go. This is actually a decision tree. So from city 2 we can go to city 4 and 3, back to 1, but we are not allowed to visit a city 2 times, so this is not an option. So these are these 2, and then this selection tree would continue to enumerate the numbers of cities we can reach by city 3. Let's have a short look. This would be 4, 5 and 7 and so forth. So the same we are doing for city 3. If we go from 1 to 3, then from 3 we can reach 4, 5 and 7. These are stated here. So this is how we can build up our first parents. And the inheritance process now works as follows. We look at, I have to mention that our genes are our links. So a gene corresponds to one link in our TSP. If we look at the first link that combines the first hometown city with a new city, we can see that for both parents we have the inheritance of the link 1, 2. If we go along, then we see that here we have next connection, so 1, 7 is part of that, or gives a link between the hometown city and another city, and parent 2 has the link city 3 to city 1. So as we are dealing with a symmetric TSP, this is 1 to 7, 7 to 1 is the same. So the options that our child now can inherit are the links 1 to 2. I enumerate them accordingly to our list here. The other one is 1 to 7, and once again 1 to 2 from the second parent, and 1 to 3 from the second parent. The inheritance process is now a random number, so that is up to some probability of selecting one of those. We see that the link 1, 2 is twice there, so the probability is of inheritance is actually higher as for the other 2. But let's assume that this link is now chosen. So our first tour would have this link. This goes on now. The next one is we look at the inheritance for city 2 to another next city. So we have here from parent 1 the link from 2 to 3 and nothing else, and from parent 2 we have the link from 2 to 4. So these 2 are possibilities of inheritance. And once again, we will have a random selection to let the child inherit either one of these links. Let's assume that the second link is now selected, and that would make our tour now 1, 2, 4, and so on. I continue a little bit. The next step, we have now city 4, so we are looking for the combinations for or links for city 4. One is 4, 3, given here. This is now getting quite dark, but yeah. So we have we need to find the combinations of 4. So 3 and 4, 4 and 3, and also 4 and 5 for the parent 1. And for parent 2, we see, well, we have 2 already included, so we are looking for links that include cities that we have not visited so far. That would be 4 and 6. So we note our options. 4 to 3, and we can flip them, so also inverse them. Then we have 4 and 5, and the next option is 4 and 6. And then once again, a random selection of which link should be inherited by the child. We randomly choose 4 and 3, so our tour becomes now 1, 2, 4, and 3. And so on, until we have all cities combined. Yeah, so this would now go on. That's how you generate children for the next combination, and then you would also include some mutations along the way of finding new populations for the algorithm. As Excel is not the right tool for implementing such an algorithm, or you can combine it with Visual Basic, then it becomes easier, but normally these kind of algorithms are implemented with a programming language like Java or Visual Basic. But in order to demonstrate how the algorithm works, we have the tutorial software. So we are selecting meta-heuristic as procedure, the genetic algorithm, and we want to look at the option of the traveling salesman problem. Here we find the number of cities for our problem and also the destinations we have, or the distances we have been looking at. And then we can do the first step, that is creating the population size. We said it would be 10. So you see in the first iteration, the best solution that has been found by by the population size, or by generating a number of trial solutions, is already 63. We know that this is actually also the optimal solution, but nevertheless, let's go on. So here you find the so-called fitness, that is our objective value of the trial solution, and here you find the children. So the green ones have been combined, for instance, with a fitness of 63, and here you can also see that a mutation has been included. So you can run this algorithm for a while, until here the stopping rule applies, that says that after 5 consecutive iterations without any improvement of the objective value, we would stop the algorithm. This is of course unfortunate now for showing the effect, because the optimal solution was already in the population. Also for the next, as said, the size of our problem is quite small, so finding 10 combinations random, even if they are the same, is quite hard at that stage.